Hey guys, this is the first video in chapter 6. It is all about light. And we start chapter 6 talking about light so we can understand a little bit about how the electron, our modern view of the electron, kind of came about. And so to start talking about that, we need to start talking about light in general. And so the first thing we need to talk about is the electromagnetic spectrum. What is light? Well, light is also called electromagnetic radiation, and we have a range of frequencies and wavelengths there. You can see all of the different wavelengths and frequencies that we have. You can see that we'll get to that in just a second. The ones that I'm really worried about, these guys right here, gamma rays and radio waves. It's kind of those the ends of the spectrum are good to know. Otherwise, memorizing frequencies and things like that, we don't need to do that for this chapter. We've got plenty of stuff going on. Now, a couple of calculations that we've talked about in class. The first one being wavelength and frequency, and the wavelength is the distance between high points or low points on a wave. So there's wavelength right there. And the frequency would be the number of waves that passes by a given point in a second. So you can just kind of imagine the number of waves in 1 second. And the nice thing about light is it always travels at the same speed, 3 times 10 to the 8 meters per second. It's the speed of light, and so if we know that, if that's always the speed, we can come up with this equation. Okay, come with this equation, and this is frequency multiplied, so frequency, this little v thing, multiplied by wavelength is equal to the speed of light, right? Wavelength in meters, so make sure you have this guy in meters. Make sure you have this guy in 1/seconds or hertz. And this guy, that'll give you meters over seconds, meters per second, 3 times 10 to the 8. So let's take a look at a calculation, what we have there. And then you see wavelength defined once again, the distance between high points or low points, and then the frequency, the number of waves that passes by a given point in a second. So really easy question, what is the frequency of light emitted by a 389 nanometer laser? Okay, so that's a laser, and we have 389 nanometers. So we know the equation that we need is this guy right here, but remember that our wavelength needs to be in meters. So we have C over the wavelength gives us frequency. So we have 3 times 10 to the 8 meters per second over 389. Remember, nanometers is 10 to the 9 nanometers in a meter, 10 to the negative 9 meters. And so there we go. So we have our conversion, we have our thing, and when we plug that into our calculator, I get 7.71 times 10 to the 14 1/seconds or hertz. Now it's important to note one thing about this. Because of how the calculation is set up, wavelength and frequency are inversely related. That is, as wavelength gets smaller, so as the distance between the waves here gets smaller, the frequency increases. Okay, so smaller wavelength gives us a larger frequency, and vice versa. A longer wavelength gives us a lower frequency. Now that's the wave-like nature of light. There was, if we talk about light as just a wave, there are several issues that we come across as far as how light behaves and why things happen the way they do. And so we had to delve a little deeper into the behavior of light. And so we're going to talk about some of those problems, and then kind of one of the final things is talk about what we came up with to reconcile those problems. So the problems, or I guess the idea here, is that we had some things we had to explain with light. And so one of the big things was black body radiation. And black body radiation isn't, for you guys on like an exam or something, it's not a terribly important concept, but it is something you do have to know kind of like why we talk about it. And basically, black body radiation is this light emitted by a warm object or by a hot object, and in all matter emits, at normal temperatures, emit some sort of radiation. That's why we can, look at like heat signatures and whatnot. Now, the idea at the time was that black body chamber should emit a high intensity of high frequency light, which it doesn't. At the same time, there was another thing we had to explain in the photoelectric effect. The photoelectric effect was if you shine a light of a specific frequency on a metal plate, it will emit electrons, and you can actually measure that charge and everything else. Now, if it was just energy, and if it's just light that was needed, we should be able to shine any frequency of light onto a metal plate, and this thing happening. Maybe over time it happens. That was a popular theory, was that if you leave the light there, it happens, but it doesn't. And also at the same time, we have these line spectrum things over here in the bottom right. And the bottom right here, what these line spectrums represent, they're the light emitted by elements. Hydrogen's got 4 emission lines, and etc. And that irrevocably tied together light, electromagnetic radiation, and the atom. And so that's where we're going next, is to talk about how light affects the atom and electrons, and how that affected our view of the atom. But first, let's take a look at what the photoelectric effect looks like. So we have a plate, we have a light source, we have a plate. When we shine that light on the plate, electrons are emitted, and we can measure that energy, or that electricity, that flow of electricity. Now, so how do we reconcile all of this? Well, Max Planck, this goofy looking guy right here, he came up with a equation, or actually really a constant that we plugged into an equation called Planck's constant, oddly enough. And we can calculate the energy of a photon by multiplying Planck's constant by the frequency. And what we see is that this maximum value of light emitted at different temperatures, and it's we can see the sun's maximum energy emission is right there in the yellow wavelength. So there we go. And that's why we see the sun as yellow, and that's actually mostly why our eyes evolved to see that frequency. So that's pretty cool. All right, so let's take a look at an example of Planck's constant in the energy equation. Now, we talked about just a second ago how to calculate wavelength, so I'm not going to go over it again, but we can definitely ask the energy of that same wavelength. From the previous question, we had a frequency. So we calculated. Remember, we used this equation to calculate frequency, and the frequency was 7.71 times 10 to the 14 hertz, or 1/seconds. Now we can take this energy and plug in Planck's constant in here, which is 6.626 times 10 to the negative 34 joule times seconds, multiplied by 7.71 times 10 to the 14 1/seconds, of course canceling out the seconds, and we get 5.11 times 10 to the negative 19 joules. And what that is one photon of light emits this amount of energy. Well, what is a photon? Well, a photon is representative of the particle wave duality of light. Basically, we explain it that light comes in packets of energy, like we saw in that photoelectric effect. It's packets of energy, not necessarily a uniform wave. Okay. So light comes in packets of light, not necessarily a uniform wave. And so we can kind of see this, that we have packets of light, not just a uniform wave like that. All right, we'll pick up next time with the Bohr model and how this affected the Bohr model, and talking about de Broglie's wavelength.